Here in this video, we will discuss the Faraday's law. And in this Faraday's law, we know that if uh, uh, and this is the experimental setup for the Faraday's law. And in this Faraday's law, this is representing the wire, long wire, and which carry the current I. And here this is representing the loop, uh, and which is connected with the galvanometer. And you know that when we pass the current through this wire, so due to the flow of current in the wire, there is the magnetic field around the region around the wire. And this uh, the direction of this field, if we place the, for example, magnetic compass near to this wire, so we can detect this field, and the direction of this field is normal to the uh, this plane of paper. So this is in the upward direction. So this is, we denoted it like this. And the magnetic hmm, and you know that when the magnetic flux uh, current is passing through the this uh, wire, straight wire, and due to this there is magnetic flux will linked through this loop, and there is production of induced EMF, or you can say the voltage is developed across the this loop. And this voltage around on the loop, we can also write this in term of the integration. This is flux phi, and here the we take the limits 0 to t, and this v dt. This is the integral, line integral. We will take this, or you can say the time integral of the voltage induced in the loop throughout the uh, interval during which the magnetic field is being established. So this 0 to t is limit is required to establish the magnetic field in this loop. Or we can say that the from this interval 0 to t, or either the magnetic field 0. So because if there is change in the, if we change the current, change in the magnetic field, and due to the change in the magnetic field, change in the magnetic flux linked with this coil, and that will give rise to this uh, induced EMF or voltage across the this loop, and that can be detected through this galvanometer. So if there is change in the magnetic field, there is the galvanometer gives the deflection. So this is, we wrote the mathematically that voltage is induced in this closed loop. We can write in term we can write the flux linked with this loop by through this equation. So if we differentiate this equation, we got the this type of uh, V is equal to minus d phi by dt, and we will call this Faraday's induction law, or you can say Faraday's law. And we know that the this is because phi is the magnetic flux which is linked with the loop, and we can write the expression for the flux in term of the integration. So we know that the magnetic flux, we can write this is surface integral, which is b dot da. This is a magnetic flux through the loop, or a magnetic flux around the wire which is linked with the loop. And we can also write the expression for the this voltage, that voltage induced in loop. We can write the expression in term of integration, so that we can write this as v is equal to close This is line integral, closed line integral, and this is equal to E dot dA, and ds is here, it is line element, and which we I have represent here. This is the element. This is line element on the loop, and we wrote the expression for the voltage induced in the loop in this fashion. So if we substitute the value of phi and v in this equation number 1 or Faraday's law, this expression we got in term of in integral form. This is the, or we will call it integral form of Faraday's law. So this is integral form. Now what we will do, that we will make the use of Stokes theorem, and we know that Stokes theorem, we can write this is equal to, for example, A is field vector A dot ds, this is line integral, which is equal to surface integral curl of A into dA. This is area element, this is surface integral. So this is the statement of the Stokes theorem. So now we use this, we will use this Stokes theorem here, and if we use this using Stokes theorem, I can write this expression of integral form of the Faraday's law, that E dot ds is equal to, I can add this, if you I use here, because this is line integral, so I if I use this Stokes theorem, I can write this is equal to, this is equivalent to surface integral curl of E dot dA. So this, and we know that this quantity is equal to this, here minus sign, this is equal to minus curly or dB by dt dot dA. So now my by using this Stokes theorem, both side now we have same type of integral. Both side I have surface integral. So we are integrating over the same area, same area, and same area element. So the on solving this uh, integration, we got this relation, that curl of E is equal to minus dB by dt, and we will call this is the differential form of the Gauss law, and this is the integral form, and the differential form is curl of E is equal to minus dB by dt. So this is the differential form of the Gauss law. So we can write the Faraday's law, V is equal to minus, this is we have studied it up to +2 level, and after in the integral form we can write Faraday's law in this manner, and in differential form we can write the Faraday's law in this form. So all three way, there are three way of writing the Faraday's law. So this is about the Faraday's law.